Thanks. Hi, welcome to Spark Your Legacy, how to distribute your 8-year-old monolith. First of all, to set the expectations, who's this talk for? If you're about or thinking about migrating existing legacy data processing jobs to Apache Spark, and mainly concerned with the methodology you should use to make this transition smooth, this is the talk for you. We did a similar project, and we're here to share our conclusions. So first of all, a little bit about us. My name is Tzach Zohar. I'm a system architect at Kenshu.
I'm Moran Tavori. I'm a lead backend developer at Kenshu.
And we've been working with Spark for the last 2.5 years, which means we started with a rather early version, 1.0, when Spark was much less mature than it is now. Things like Spark SQL didn't even exist. So it's been kind of a joyful ride to join this open source community and find out that we actually chose the right horse when we made that decision back then. A little bit about Kenshu. We are a 10-year-old Tel Aviv-based startup. We've been named industry leader in digital marketing. What that basically means is that we provide technology for some of the largest advertisers online to automate and manage and optimize their online campaigns. And when you talk about online digital marketing, obviously you talk about large scales. Modern, large online campaigns contain dozens of millions of entities like ads and in search keywords and stuff like that. And each of those has dozens of metrics that you have to follow in order to make some, to get to some conclusions and automate and optimize the campaign management. So we are a very heavy data shop. Data is part of what we do. It's part of what our clients expect us to do well, and part of the differentiator that we have compared to some of our competition. So this is where obviously Spark fits in quite well. Let's discuss the problem that we had at hand, and we're here to discuss. We had a legacy system that one of its jobs was an aggregation job over these advertising metrics. So let's see some of its characteristics. The job performed aggregations while applying some complex business rules that kind of were added over the years. Again, it's an 8-year-old application, so it gets more and more complex, and things just get added as time goes by. But this specific job performing these aggregations wasn't just a standalone Java application. It was part of kind of our first application, a monolithic Java application that also ran hundreds of different jobs, doing lots of different stuff, either related or not that related to what this specific job did, and all within the same application. So obviously, when you have this kind of architecture, you end up with some coupling between separate pieces of code between these specific aggregation jobs and other jobs that might not be related. They share the same code base and share the same database and maybe memory and the same JVM. All of this was sharded by client. We had to scale, and the solution was to just create this instance of this monolith per client or group of clients, which gives you some flexibility. It's easy to grow at the first phases. That's what many startups do. But obviously, if we have a problem with a specific job, like this aggregation job, and you want to give it more resources, you can't really do that just for this job. It's a single application doing lots of other things. So if you want this job to handle more data, or one single client gets too big, it's getting too hard to scale. And this is the problem that we set out to fix. And obviously, when you have such problem, when you think about scalability and gaining some linear scalability with additional resources, you think about distributed processing frameworks such as Spark. So back when we started this project, we thought Spark was an interesting option, and we decided to try it. We performed a short POC, a proof of concept, where we tried to implement a subset of what that specific aggregation job does, some simpler version of that job, to see whether Spark fits our needs. And indeed, we were very happy to see that the API was very well suited for our use case. It was very easy to kind of articulate what we had to do using Spark's API with very little boilerplate, which is one of the benefits Spark brought in the very beginning compared to things like Hadoop MapReduce, not too much noise around the actual code. And it was very testable, which was also very important for us. So the POC, these are all straight out of the POC conclusions, and it did show that it shouldn't be too hard to just implement this job using Spark. However, our problem wasn't really just implement a job using Spark. Our bigger problem was how to migrate an existing legacy job that's been written over 8 years and is part of a larger monolithic application into Spark. How to make that transition safely.
Well, when rewriting an existing system, you have two main options. The first option is to go greenfield, to take your existing system, start rewriting it from scratch, and eventually, once you're done, switch the old one with the new. The other option is refactoring. You'd first make sure that your system was well tested, and then you'd start introducing small changes. And each of these changes will be deployed to production to get feedback before you move on to the next change. Now, we've been practicing agile methodologies for a while now, as some of you might have. So we know that we should always prefer refactoring. It's a gradual process and therefore much safer if done right. The only question is, can it be done in our case? Can we take our existing single server system and refactor it to a distributed solution over Spark? How can we make the jump? There's a paradigm shift here, a gap that cannot be bridged over by gradually refactoring our code. We're either running on a single server or in a cluster. This transition cannot be broken into smaller phases. So maybe greenfield is our only valid option here, but since switching one system with another is a big risk, we want to find a way to do that while minimizing this risk as much as we can. So in the rest of the presentation, we're going to talk about the main issues we found in a greenfield project and the solutions we've come up with. Now, some of these solutions are specific to Spark, and some can be reused regardless, but we found especially useful when transitioning to a Spark-like solution. So the first problem is our spec, or lack thereof. Now, remember, this is a legacy system we're talking about. So we don't have a clear spec defining what it should do at any given time. But we do know that it's working, and that our new system has to work the exact same way. So we don't have any choice but to look at our code and try to derive a spec out of it. And in some cases, this is very easy. You can see that given A, we need to return B, and some of the code is very well tested, and the tests describe what it does. But in other cases, this is much more complicated. The code may not be as readable, it might not be well tested, and it might not even be deterministic. So let's take a look at one example of such an issue we had to tackle. Now, this is an unedited piece of code from our legacy system, which handles some kind of a channel object. It's not important what a channel is. And as you can see, we have here a check, which in the case the channel is null, which shouldn't happen. We need to return a best guess. And this best guess is, if this channels list isn't empty, we need to return the first item on that list. So as you can see, this is a tough one. What is this channels list we're checking? Is it ordered in a certain way? Do we need to return the same item every time? And most importantly, do we need to return the exact same item in our new system as well? Or maybe this really doesn't happen, as it shouldn't, and we don't have to worry about this. We don't have to rewrite this in our new system.
So you are suggesting that we just ignore the case where the channel is null and assume that it never happens and risk null pointer exceptions down the road?
Well, when you put it that way, maybe not.
The conclusion that we came to, which also became kind of our motto, was don't assume, measure. Whenever the code is not explicit and whenever a code comment might contradict what actually happens, just measure what really happens using production data and don't assume that code comments or even common sense can tell you anything about what the code actually does. So in this case, we performed something that we called empirical reverse engineering, which means we empirically, using production data, kind of reverse engineer the pieces of code that we can't figure out to get some information about what actually happens, and so that we can make the choice and we can implement the new version of this code. So in this case, if we focus again on the just get the first one use case, we refactor this piece of code into something that currently does exactly the same thing, performs the same guess. It's just encapsulated in this get any search engine channel data function, just to be a bit nicer. And if it did guess something, we would now log an error and also count the number of times this happens. We count using a nice Java library called Drop Wizard Metrics. It's a very lightweight, very easy to use library for publishing metrics out of your JVM, out of your Java application. And we send all the data into Graphite to get nice graphs over time of these counters. So we perform this refactoring in our old legacy system. We deploy this to production, and we expect to see this counter remaining 0 because this shouldn't happen. But not that surprisingly, it does happen, and it actually happens a few times a day on various of our servers. And this gives us a pinpointed point in time that we can go look at the logs and find these occurrences. And when we did, we actually found out that one specific feature that was added a few years ago, but a few years after this piece of code was written, was actually relying on the fact that some channel was returned. It didn't really matter which one, apparently. So we could now drill down and understand exactly when this happened, for what reason, what was it used for, and implement it more explicitly without any guessing. Now that we know what it's intended to do, we can remove all the guessing and all the doubt and all the assumptions and just implement an explicit version of this code that we can use both in the old system and in the new one. So we had a few of those, and we just cleaned them up using this technique. The next problem that we had to face is kind of the classical greenfield project issue, and also a very self-explanatory one, the moving target issue. You start with a legacy system. You want to replace it with something that does exactly the same, but using maybe different infrastructure. So you take a team, you start coding, and after a few weeks or months or whatever, you have a new version, and you're ready to make the switch the old one off and the new one on. But by the time you did that, the legacy system has moved on, maybe bug fixes, a few new features, whatever it was. Now you can't really make the switch because the new system does something slightly different than the old one, which has moved on. So obviously, you just look at these changes and implement them into your new system. But by the time you did that, maybe a few more changes were introduced into the old one. And this becomes kind of a race that some companies didn't even survive. And it's hard to know that you are at a point where you can make that switch. So how can we win this race?
Well, we decided we're not going to go down this path. We're not going to rewrite our entire business logic from scratch. What we did instead is refactored our core business rules into a separate jar. And this jar is now shared between both our systems. So now if anyone wants to make any changes to the legacy system, it has to be done in this shared jar and will be immediately applied in both our systems. So now what we have are two different containers running the exact same business logic. But are we able to reuse our business logic as is? Our legacy code is imperative Java code, and our Spark solution requires our business logic to be functional. Spark's API lets you reuse any arbitrary function, just as long as it's a pure function with no side effects. But that's not something you see in an 8-year-old Java application, and it wasn't in ours. This is what our system used to look like. So you can see here we have a collection, which we iterate over and filter by applying a couple of conditions. And these two conditions are ones we'd like to share with our new system. But as they are right now in the current state, they're coupled with the iteration they're in. So before we will be able to reuse them, we'll need to decouple them from the iteration. So we did just that, and what we have now is a single function, a should aggregate score function, which takes a key which contains all the metadata it needs for the check it performs. And this replaces the two conditions we saw in the previous slide. And our legacy system, once we refactored it, looks like this. We still have the same iteration, and we still filter the collection by applying the now refactored should aggregate score condition. And our new system looks very similar to this. In our new system, we of course have an RDD instead of the collection, and we filter it by applying the same should aggregate score function. So the first phase of our project was to refactor our business logic into pure functions. And now what we have to do is start our greenfield project around this already proven business logic. And this is really great. This brings our new system much closer to our legacy system, which minimizes the error margin by a great deal. But minimizing isn't good enough. We have zero diff tolerance for our new system, meaning if for any given input our legacy system used to return a certain result, the new system has to return the exact same result. Why? Well, there are other modules in our product which use our data. And since these modules are a part of the same legacy system, there's no defined contract between these and our module. So we don't know how they expect our data to look like. We don't know if they make any assumptions regarding our calculations. And if we change our calculations, even if we only change the rounding method we use, we might cause unexpected behaviors in these modules. And we don't want to do that. We don't want our colleagues as angry with us as this guy. So how can we meet such a strict requirement?
Well, the first thing that comes to mind is just running the two systems side by side and comparing the results, and that's something we did. So you have, instead of just switching the old system on and off at the same time you switch the new one on, you split your data, you duplicate everything, and you run everything in both systems, and you automate some process that compares the results of the two systems for a while, which then creates reports like the one we see here. And in the red box, you can see an example of an actual rounding issue that we had. You see the numbers are almost correct. So we had to go and fix that and some others that we found this way. But this is limited. This has a few issues, this technique. The first one is the scale. The reason we started this project was the fact that the old system was just not keeping up with the scale of the data. So now this not only means that we have to keep it alive for a bit longer, it also means that we need enough resources to run both the old one and the new one, and some more resources to perform the actual comparison. So it's a bit expensive when you talk about big data. Usually you just end up with comparing just a subset, a sample of the data for just a few clients or a few days or whatever. So we decided to implement this concept of side-by-side at a much lower level, something that would limit the scope of the data that we have to handle. Another issue with this is the fact that it does bring out all the issues. It shows that the end result is not the same, but it gives you no pointers as to where this difference comes from. This looks at the two systems as two black boxes producing outputs. You look at the very end result, and it's not the same, and now you have a whole system to investigate to understand where this comes from. So both of these issues were solved by applying this side-by-side concept at a lower level, at the component level. We already said that some of the code was shared. Okay, we had these pure functions, a library of pure functions that we can use in both systems, so these were okay. We could safely assume that they do the same, but some components we did have to rewrite. Specific components in the old application, we completely rewrote in favor of the new one. Maybe because they were relying on infrastructure that we didn't use in the new one, like MySQL and stuff like that. And maybe just the implementation wasn't good enough and we wanted the new one. So we ran this new implementation of this specific component side by side with the old component. And we often did that using the composite pattern. So this is an example, a real example from our code. We had a desired source resolver, one of the components in our system, a Java interface, and we had an old implementation. And we created a new implementation that we wanted to test. We wanted to verify that it does exactly the same thing. And for that, we created a third implementation, which is what you see here, the composite implementation, that has two members, which is the old implementation and the new one. The old would be the active, and the new would be the passive. And when you invoke that interface's single method, it invokes both implementation, the old and the new, returns the result from the old one, which is what makes it active, because we trust the old one, we know it's correct. But before this return, we record any differences if there are any. So this, after we deploy this to production, we'll be able to know if there are differences, and if there are, what exactly are there. And in this diff recorder, we again use drop wizard metrics with graphite to get a nice graphs of these matches and differences. And indeed, we had a first draft, a first implementation of the new version of this interface. And not too surprisingly, there were differences. On the left side, you can see in green the total matches. So we were mostly right, but at least 10 or 15% are the red ones, which are the differences. But the metrics were granular enough to give us some information as to where the differences come from. What was the input for which we gave different results, and what were the two different results. And an example for this you can see in the right-hand graph, when we dissect the differences by various parts of this information. In this case, the old result, by the result produced by the old implementation. So this gave us enough information to go and hunt down every difference, every bug that we had in the new implementation that didn't behave like the old one, until the left-hand side graph was completely green, and then we know the new component is completely equivalent. We can just replace the old one with the new one and get rid of this composite one, both in the old system and in the new one that we are building. The last issue that we wanted to discuss is reusing tests. Our legacy system was legacy, but it did have some actually quite extensive suite of tests, mostly behavioral tests or end-to-end tests that tested this batch job. Create input, run the batch job, validate the output. And obviously these tests should also pass for the new implementation. We keep discussing the fact that they should be identical in functionality. So it would be great if we could just run all these tests for the new implementation and make sure that we stay on par with the old one. However, there's a technical issue with reusing these tests. The tests are part of the old legacy code base. When we execute them in the old system, it's just in process. The tests create data, invoke the batch job by just invoking some Java function, and they can see the results, and the test is done. That's quite simple. In the new implementation, though, the tests remain in the old code base. But as we said, we started a greenfield project. So the new implementation of the aggregation system is a separate Java process, a completely separate server maybe, or container or whatever that has to be set up in order for the test to run. And it doesn't end here because this is a Spark-based implementation. So theoretically, there should also be some Spark cluster just waiting for these requests to come in, or maybe each test should start a cluster and then turn it off at the end. No matter how you look at it, this is a messy setup for a test. Tests that are built like this won't be fast enough, won't be reliable. We can't really use them. So how can we get rid of all these red arrows?
Well, the last part is kind of easy. We use Spark's local mode, which runs embedded in our legacy system. And we don't have to worry about any cluster for our tests. And actually, Spark's local mode is such a great tool, and it's so easy to use, that we decided to use this as our model and created our own local mode. And our local mode runs embedded in our legacy system, so we don't have to worry about the communication between the legacy system and our new aggregation system. And that's really all there is to it. There's no extra configuration or setup needed. We get to immediately reuse our entire test suite that we had for our legacy system. And these tests can run from any machine, any dev machine, any CI server, whatever is needed. So we've seen that sometimes you have to go greenfield, but that doesn't mean accepting all the risky implication of rewriting your existing system from scratch. Spark's Fluent APIs makes it possible to share code with your old system. Spark's local mode makes testing easier. And other common agile practices like short feedback loop and gradual rollout lets you control the process and get feedback from your system before it's client-facing. Now, the solutions we discussed might not fit any rewrite project out there, but we do believe that finding the middle way between a greenfield project and refactoring your existing system is the safest, fastest way to replace one system with another without ever changing its behavior. Thank you.
Thank you.
Awesome. We have time for a couple of questions.
I was wondering if you considered using the local mode in lieu of the cluster when you were going through the process of proving equivalence, just running it that way.
We did use local mode for any tests of the new system. All of our tests for the new system, regardless of the old one, use local mode, which is, I think, what everybody does when using Spark, but nothing outside of that. It did prove useful, though.
Any other questions? All right, let's give him a big hand.
Thank you.